Now we're going to talk about what does temperature changes or heat transfers have to do with anything. One of the changes that increases entropy was an increase of temperature. So let's talk about what temperature and heat transfer has to do with anything in terms of entropy. Specifically, what does it have to do with entropy of the surroundings? The second law demands that entropy of the universe increases for a spontaneous process. But when we think about some of the spontaneous processes around us, condensation of water vapor is sometimes spontaneous, even though water vapor is more random than liquid water, right? If you boil water and then you stick your hand on top of the pot that's boiling, water vapor is going to condense down on your hand. Why does it do that? If technically going from a gas to a liquid is entropically unfavorable, but it's still overall a spontaneous process. It's because we have to consider the surrounding entropy as well. All right, so if a process is spontaneous and the entropy change of the system is technically unfavorable, there must have been a large increase in the entropy of the surroundings. And the entropy increase must come from heat released by the system. So the process must be exothermic. This link is going to be very important where our delta H is going to be linked with delta S of the surroundings. So a process that is exothermic is going to add heat to the surroundings, and that increases the entropy of the surroundings. When a system's process is endothermic, it takes heat away from the surroundings, and that decreases the entropy of the surroundings. So what we're seeing here is an opposite effect. As heat is released by a system, it's going to be going into the surroundings and vice versa. When heat is absorbed by the system, it's coming from the surroundings. We knew this, right? But now what that temperature change, what that heat change is going to be able to do is affect the entropy of the surroundings. The amount of entropy of the surroundings is going to depend on the original temperature. The higher the original temperature, the less effective effect addition or removal has, right? So there is going to be a cap on how much temperature is going to be added. The entropy change in the surroundings is going to be proportional to the amount of heat gained or lost, right? We know this is true right here. The heat from the system is the same magnitude but opposite sign as the surroundings. So the entropy change of the surroundings is also inversely proportional to the temperature. And what we come up with is a calculation for the delta S of the surroundings. Delta S of the surroundings is going to equal the opposite sign negative delta H of the system over temperature. This is an important discovery because it will actually help us to quantify the entropy of the surroundings. Let's do a quick practice problem. Let's look at this combustion of propane again. We've looked at this a couple times already. It has a delta H written there as negative 2,044 kilojoules. We're going to calculate the entropy change of the surroundings associated with this reaction at 25 degrees Celsius. And we are going to also determine the sign of the entropy change for the system. We don't know how to calculate the entropy change, quantify it yet, but we can qualify it with a sign. And then we'll determine the sign of the entropy change for the universe. Is the reaction spontaneous, right? So first step, A, the delta S of the surroundings is equal to the negative delta H of the reaction over temperature. Temperature here needs to be in Kelvin. Why? Because degrees Celsius has negative values. We have to, for all of these reactions, convert to Kelvin. So degrees Celsius plus 273.15 equals Kelvin. All right, so negative of the negative, right? I want to make sure I keep all of my signs correct here. Kilojoules divided by 273.15 plus 25 degrees Celsius, 298 K. That delta S of the surroundings is 6.86 kilojoules per mole Kelvin. Sometimes the kilojoules per mole part, the per mole, is sometimes dropped off, just like it is for delta H. So you can say 6.86 kilojoules per Kelvin as well. But note, it is positive. The delta S of the surroundings is favorable, increasing. B, let's estimate the delta S of the system or the reaction by looking at the overall reaction. Okay, so we have gases, everything's a gas, so no state changes. We have 6 moles on the reactant side and 7 moles on the product side. That's a positive. Thinking about increasing the number of moles of the system on the product side, that means entropy is favorable for the reaction. Delta S of the universe is equal to delta S of the system plus delta S of the surroundings. If both of these are positive values, then we are going to get a positive value for the delta S of the universe. Delta S of the universe is positive, the reaction is spontaneous. Yay! And there was much rejoicing. Again, it will happen on its own. Will it happen fast or slow? We don't know yet. All right, temperature dependence of delta S of the surroundings. When heat is added to the surroundings that are cool, it has a lot more of effect on the entropy than it would if the surroundings were already hot. So water freezes spontaneously below 0 degrees because heat is released on freezing and increases the entropy of the surroundings enough to make delta S positive. So when we're looking at the temperature idea, all right, adding temperature to an already exothermic reaction is probably not going to be that big of a deal, but adding temperature, adding heat to an endothermic reaction is a big deal. All right, so we'll see this play out a little bit in a little bit, but when entropy change in a system is unfavorable, negative, the entropy change in the surroundings must be favorable and large in order to allow the process to be spontaneous. It's the balance between both of these. If one is negative and the other is positive, the positive one we want to be large positive in value, because then that will kick us over to have a delta S of the universe as positive. All right, we're going to talk about what a standard condition is again real quick. We remind ourselves of standard enthalpies. We have standard entropies as well. So just as we had delta H with the little standard, delta S also appears in the little standard state. Gases mean it's a pure gas at 1 atm. Solids or liquids means it's a pure solid or liquid in its most stable form at 1 atm and 25 degrees Celsius, and a solution of 1 molar. These are all different states that we would have to be considered what's the standard state of that solid, liquid, gas, or solution. Bringing up the third law of thermodynamics real quick. The third law states that for a perfect crystal and at absolute 0, the absolute entropy is 0. And that helps us identify the temperature at which entropy is going to be a standard 0 joules per mole Kelvin. Therefore, every substance that is not perfectly a crystal at absolute 0 has some form of entropy. And therefore, the absolute entropy of a substance is always positive, because a perfect crystal is the most ordered state that we have for a substance. And that means that anything slightly disordered, anything less than perfect, would have a positive entropy. So standard absolute entropies are positive. The entropy is an extensive physical property of matter. And so entropies are for 1 mole of a substance at 298 K above absolute zero, right? And so for a particular state, an allotrope or a molecular complexity for everything, these entropies are going to be listed on a table. Delta S, the change in entropy for a reaction, can be utilized or discovered with these standard states, just like before, products minus reactants, okay? Now they are all going to be positive in value. So that's something that we would see that's slightly different than our delta H's at standard states. The delta H's of formation we used in chapter 9 could be positive, negative, or zero. Entropy here, because of how it's defined, the entropy at a standard state will always be positive because it's not in a perfect crystalline structure at absolute zero. These are temperature dependent. And again, the same idea when we calculate delta S this way, if delta S of the system is positive, the overall reaction is entropically favorable. If the delta S of the system is negative, then it is not entropically favorable. Relative standard entropies. So when we're looking at a gas state that has a larger entropy than a liquid state, we can see that in the delta S's at the standard state. The liquid state has a larger entropy than the solid as well. So we can just see that relationship here. Gases will always have a higher entropy than the liquid form. Now we have numbers to it, right? Here are some other standard entropies that we can see. This table is in your textbook. There is a wide variety of entropies. If you need these numbers, I would give them to you. We do need to know how to qualify delta S. So thinking about if the sign is positive or negative based off of the number of molecules or the states themselves in the reaction, that's important. If we wanted to quantify things, slap a number on it, do the actual equation, I would give you these numbers, all right? Just to highlight a few more to make sure that we know the idea here, the larger the molar mass, the larger the entropy. So as we go down a group on the periodic table, we get an increase in mass. The available energy states are more closely spaced. And as we think about the larger atom, we are allowing more of a dispersal of the energy throughout those states. We have a bigger electron cloud, we have more options for the electrons to be in, etc. Allotropes. These are looking at diamonds versus graphite. So allotropes are a specific element that exists in more than one structural form in nature. Carbon graphite is the most entropically favorable. We see it's a 5.7 joules per mole Kelvin. And that's why we technically see graphite as more prevalent than diamonds. Graphite is less constrained. It has sheets of carbon atoms rather than a crystalline structure. So finally here, we're going to use this equation, the exact same as what we had for delta H, right? We'll give you a chart, we'll give you a balanced chemical equation, and you can plug in the delta S's for the products minus the delta S's of the reactants and be able to determine overall what is the estimated delta S of the reaction. So now we know how to calculate delta S of the surroundings based off of enthalpy and the temperature. And we know how to calculate delta S of the reaction. So we can talk about spontaneity a little bit more. And we will continue on this idea throughout the rest of the week.